Okay, here's, like I say, here's what I'd really like to do. I'd like to get you going in the lab. We've been in here many days, and I think I'd like to get you doing some work. Okay, one kind of last thing we got to wrap up, and then we're ready to, I can give you a new assignment. You can go work on that and maybe work on some of the old stuff if you want to retake a test, etc., etc. Let's kind of quickly just debrief what we looked at in the last week. We closed up, we took this example where we had a function f of x equals x squared. We wanted to add up the area under that curve from x equals 1 to x equals 4, right? And we did this with 30 slices. We cut it, just kind of arbitrarily cut it into 30 pieces. And this is where we started. Now, do you remember, there's a couple things that I want to just point out about this. We want to make a generalization. And then ultimately today, what I want to close up with is just looking at how we might have done this without saying let's let n equal 30. Let's just keep it in terms of n. Let's just write an expression in terms of just some random number of slices n that we could control later. When we get done, we'll get a formula in terms of that n, the number of slices. And the area that we calculate will be a function of that parameter n, how many slices we decide we want to have. And then the more, if we need it really accurate, we can make n be a big number. If we don't need it as accurate, we could let it be a smaller number. And we'll even talk about how we could have it be perfect, how we could have it not really an approximation, but an exact accounting of the area under the curve. Okay, so first of all, this was really key right here. This was probably the hardest part, and this was the most important part. That's how, remember what that meant. We drew this picture, and let me go back one here, I think, so we can see the picture, too. Right, here's our picture. And we wanted to come up with an area of the ith rectangle. Okay. Now, for us, what we did is we calculated the circumscribed rectangle because we were using, for the ith rectangle, for the ith subinterval, we were using its right-hand edge to determine the height of the rectangle. Right? If we had used the left-hand edge, then we would have been calculating the inscribed rectangles, but we ended up calculating the circumscribed ones. Okay? Now, I don't want to spend too much time because you're going to see pretty shortly that it really doesn't matter if we're using inscribed or circumscribed, because if we get the limit to become exact, what difference does it make? If we can pick enough of these things, the area, the extra area just shrinks to 0, and it doesn't make any difference where we started, right? But we could have some control over whether we wanted to pick inscribed or circumscribed just by switching between using the right-hand edge of this interval or the left-hand edge. Okay, we used the right-hand edge, and honestly the reason I used it is because algebraically it's just a little bit easier to do. And this is what it looked like, right? It was, there it was. Okay, I'm going to grab this and go back to that. I want you to tell me real quick here, how could I have maybe done the same thing but with the left-hand edge? How would I have to change this formula? I minus 1. Yeah, that's really all we have to do. Exactly, that's all we have to do is every place we have an I, we'll just switch and replace it with an I minus 1. And, well, there it is right there. Right there's, well, there it is right there. There's our formula, right? So this is what we might call the formula at the right-hand edge. And a lot of times, there's all kinds of, I've got a handout that I'll probably just give you, just so you can see it. But it's really overkill. It's, I mean, it talks about how we could change the notation to indicate if we're, like, we could call this A sub R, and we could call another one A sub L for the left-hand side. If we want to call that A sub R, then A sub L would just be A sub, well, it's maybe still A sub I, but if we wrote it this way, in terms of a function, it's just going to be f of A plus, and where I used to have an I, all I have to do is just put in an I minus 1. Because instead of taking that extra step, we start at A, we're going to go one step, that's 1 delta x, 2 delta x, etc. Instead of stepping over one extra step to the right of that interval, we'll just stay on the left-hand edge, which is the same thing as the right edge of the previous interval, right? So that's the only difference we'd have to do is just replace that I with an I minus 1. But everything else would stay exactly the same. So if, I can't even remember if you ever even have to do that on these assignments. You maybe have to do it once or twice at the most. But that's how we could do it if we wanted to control where we were calculating the height, the right or the left. And remember, for us, because this was an increasing function, the right-hand edge was the higher of the two edges, right? And so that was the so we did circumscribed stuff. If this had been a decreasing function, the right-hand edge then would have been the lower of the two functional heights, and it would have given us the inscribed. Okay? I don't want to get too hung up on that stuff. So let's just do this then for today. Let's look at our example that we did, and let's kind of repeat it. But this time, let's do it without specifying n. So a lot of the algebra is going to look very, very similar to what we did last time. So if our function is, and let's just for review, how about if we just kind of start. Start on a clean sheet of paper here. And okay, so let's come up with the area of the ith subinterval, and then we'll just sum them up to get the whole area. Okay? So if we're doing the right-hand edge, what did we say that was again? We've got to do the height times the width. Well, the width is easy. The width is just delta x, right? And delta x is, how do we define that again? Do you remember from last week? The width of each subinterval, and have the whole width. Okay, b minus a divided by n. I'm going to have the whatever the biggest x value, the ending x value minus the starting x value, so the entire width of the interval divided by the number of slices in. So for us, this is just going to be, well, so that's 3 over n, right? So that's the width of each individual rectangle, and the height we said was determined by the right-hand edge, the height of the function at the right-hand edge, right? So f of, how do I say the right-hand edge again if I'm starting at A and I'm on the ith subinterval? Good. A plus I steps of delta x width, right? So A plus I delta x, that's the x value of the right-hand edge. Put it into the function to find out how tall the rectangle is. Multiply through by delta x. Okay. Well, if we get specific then, our function is x squared, a is 1, b is 4, delta x is 3 over n. Right? So this would look like f of 1 plus I times 3 over n, just 3i over n, right? Times delta x is 3 over n. And if f of x is x squared, f of junk is junk squared. Okay, so a sub I is the quantity 1 plus 3i over n squared times 3 over n. Okay? So we got to sum those up then. And we got, there's the area of one of them. The total area is just going to be the sum of all those guys. Up to n. Right? Whatever n is. I'm just going to write all this stuff. I'll just write a sigma and we'll know what it is. So sigma, this stuff. So what do I do algebraically?
Go term by term.
Say it again.
Term by term.
Going to go term by term. Got to expand this out, right? So, and notice that maybe I will write this one time. I probably should just write it. Okay, I is the only thing that's going to change in this sigma, right? The sigma is summing up I. All the other stuff, even though they may be variables or they may be things that we're going to take limits with later, I is the only thing that the sigma cares about. That's the variable of summation, or the index of summation. So if we boil that out, what do we get?
1.
Okay, I'm going to get 1 plus,
6i.
okay, A, if that's A and B, and we do A plus B squared, we get A squared plus 2AB, so we get 6 I over N plus
9 squared.
9
No. Yeah.
I squared over N squared, good. All times 3 over N. Okay, now here's where we can break this up term by term, right? And remember, we had a whole bunch of summation formulas that we're able to fall back on now. So just right back here somewhere. There. Right? Okay. And so by just using those formulas, we're able to actually take those sums and get answers in terms of n, which we haven't pinned down yet. Okay, so we can end up writing this as the sum of, and if I distribute this 3n all the way through, I'm just going to get the sum of 3 over n times 1 plus, what is that, 18 over n squared, the sum of that times I, plus right? Okay. Okay, and then remember, being as I is the variable of summation there, everything else is a constant. And what can we always do with a constant in a sum?
Pull it up.
Yeah, we can pull it out front because that's just going to be multiplied by each value of I, isn't it? So it's going to be a common factor that we could factor out of each term in the sum. Okay. And so this first one, then we just get 3 over n times the sum of 1 terrible sigma. Sorry about that. 18 over n squared times the sum of I plus 27 over n cubed times the sum of I squared. And we have all those formulas. What's the sum of 1 from 1 to n? 1 plus 1 plus 1, n times, right? What's that going to be? N. Yeah, n. Right? So I'm going to get, so this first term is going to end up being 3 over n times n, and the n's will cancel. Plus, how about this one? Well, we're going to get our 18 over n squared. Do you happen to remember what the sum of I was? Yeah, good. N times n plus 1 over 2. That's right. Plus Yeah, this one was what? N times n plus 1.
2n.
Okay? So now we got an answer. We just have to kind of do a little algebra and maybe make this thing look a little nicer. Well, this is good here. We can cancel those, right? And so our first term just looks like 3. Now what about the second one? We can do a little bit of cancellation. Why don't I cancel one of those n's with one of those guys, right? Then the 18 over 2, good, that becomes a 9. So this one's just going to be 9 times the quantity n plus 1 over 2.
We still have an n under 2n.
Oh, whoops, over 2n. Yeah, you're right, over 2n. No, I don't have the 2 there either, do I? Whoops. Gotta go back. There we go. That's what we have. Agree? Because that went away and that became a 9. Okay? Plus, let's see here. So I can go 9 and 2, right? And I could cancel one of those n's. So you get an n squared on the bottom. Okay, and then if I were to FOIL that out, so I'm going to get 9 halves times, if I FOIL that out, I just get 2n squared plus 3n plus 1 over n squared. See where I get that? If we're just taking this stuff right here divided by the n squared. Okay? So now let's maybe add up some like terms. If I expand this part out, I get 3. If I write this as 2 separate fractions, that's just 9 times 1 plus 1 over n. Everybody agree with that? So that's just going to give me 9 plus 9 over n if I distribute. Okay. What about here? I'm going to get plus, if I expand this whole thing into, or break it apart into 3 fractions, isn't that going to look like, let's just actually do that. We're going to get, the n squareds will cancel here, so I'm going to get 2 plus 3 over n in that middle term, plus 1 over n squared. Okay? And if I distribute that 9 halves, that's just going to give me, what, 9? So 2's will cancel, plus 27 over 2n, plus 9 over 2n squared. And then if I add all this stuff up, this is looking kind of ugly, but we're getting there. How many, what if we add all the constants up? I've got a 9 and a 9 and a 3, so 21, okay? What about the n's on the bottom? I got to get a common denominator, it looks like, huh? So I'm going to have 27 over 2n plus 18 over 2n. I can turn that into an 18 over 2n. Right? Gives me, what is that, 45 over 2n? Plus, and then the last one would just be 9 over 2n squared. Okay, well that's pretty good, right? We got the area. So the area was just a sum of n rectangles, and that's what we got, right? Our formula is now a function of however many rectangles we choose to use. If I just use one big rectangle, and I tell you what, let's put this in our calculator to make a table, and see what this looks like. Okay, so. Calculator. Okay, now we can't use x conveniently as a value of, as a variable in here, right? But what we can do is we could use x. We could use, can't use n, but we can use x. So let's write this formula with x's instead of n's. So 21 plus 45 over 2n. Oops. Okay, right? Everybody buy that? Okay, so there's our formula. If I put it in y1, then I can just go to the table and let it generate table values for me for all the different values of n, which we're calling x. So I'm going to make sure my table is set properly. I want to start at 0, go by 1s, perfect. So, okay, so let's see what we get. If it's given these, oh, that's kind of unfortunate. It's given to these to me in fractions.
Like 400 something. I'm at 21.05.
Yeah.
Still going down.
Yeah. Let me do, I hate to waste time. I'm going to do one thing. I think the reason it does that is because I wrote those using that fraction template. So there's the argument for not using that fraction template, I think. So I really kind of want to look at these as decimals. Don't those go away? There we go. There we go. Finally. Okay, so what I have, 45 divided by the quantity. Let's just do it this way. If we just do it this way, I think it'll give us decimals. Divided by the quantity, 2x, plus 9 divided by the quantity, 2x squared. Okay, now if I go table, yeah, that's what I want. Okay, now it's giving me decimals. So if I only use one rectangle for the whole thing, well, the rectangle is a pretty poor fit for the area under a parabola. So that's a horrible, horrible guess. But as the number of rectangles increases, pretty quickly you can see this number dropping down. And if I just scoot down the list, getting better. What value do you suppose it's going to be approaching? Anybody tell me?
21.
Yeah, 21. Still not there. In fact, it's never going to be there on this list because this is a finite list. Although out to the number of decimal places that it's going to give us an answer, it may get there. But we got to go quite a ways, don't we? I mean, now we're up to 59, 60 rectangles, 61. And we're getting close, but it's still up at 21.37. I'm getting tired of this. Can somebody tell me what's a shortcut? How can I get to that exact answer much more quickly?
Can you type in numbers on the table? Like, can you type in actual numbers?
That's a good question. Let's try it.
What, like,
Well, here's what you can do. I don't think you can do that, but here's what you can do. You can go up to second table set, and you can choose the starting value for your table. So I could start at like 600 or 6,000. At 6,000 is 21.004. Okay. Now I'm getting tired of this. You got to come up with a better way. How can I just get an exact answer? 6,000 seems like a lot, but it's not very much compared to a billion.
Approaching infinity, right?
Ah, say it again.
Approaching infinity, but it never touches it.
Okay, so why don't we do this? Why don't we find out what the answer to this formula is as the number of rectangles approaches infinity? Because as the number of rectangles approaches infinity, isn't our answer going to approach perfection, right? And think back to that the little game we played up here with that applet where remember when we dialed up the number of rectangles, how much better the rectangles fit the curve, right? So let's try that. What if we just do this? What if we say that the exact answer must be equal to the limit of a sub n as n approaches infinity, right? Well, that's the limit of just this stuff, right? Now, what's going to happen to those two fractions? What's going to happen to 45 over 2n as n approaches infinity and the denominator in that fraction gets infinitely big? It's going to approach 0, isn't it? Yeah. Right? So this one's going to approach 0. 9 over 2n squared is going to approach 0 even faster. And so our only answer is going to be the 21. Right? How cool is that? Right? That's pretty slick. So the answer is exactly 21. Guaranteed. Okay. So to summarize, what did we do that was so tricky? All we did was, when we set up our area calculation for n rectangles, that inevitably gave us, when we summed up our all these terms, right? We got some formula, some area formula based on what our function was, x squared, right? Remember, junk squared gave us this stuff, right here, right? When we squared out the area of the ith rectangle, whatever that expression was. And then we get this sum in terms of i's, but we got n's in there. And so once we clear out the i's, once we sum these things over I and use our summation formulas, right? Remember, sum of I is, for example, n times 2n over 2, etc., etc. And we turn this into an expression in terms of n's, we probably didn't have to waste all that time even collecting all these terms, did we? Right? Because if we want to get an exact limit, all we have to do is, our exact answer is take a limit of our answer as n approaches infinity. So all we really had to do in this problem was get down to this point right here where I reduced the fractions. So I had constants and constants divided by some power of n. And then if I had just taken the limit right here, I could have seen that, well, this term right there would have gone to 0. That term would have gone to 0. That term would have gone to 0. And I would have ended up with these stragglers remaining, all these constants. Add those up and get 21. See how that works? It's in a way, I kind of went through that in a mundane way, and it just looked like another example, but that's huge. That's possibly the coolest thing we've ever done right there. That's pretty amazing, right? So there's the trick. There's the trick. You can calculate an exact limit, and it doesn't, as we're going to say, I'm going to put this thing to an end for today. I feel like I've given you a lot of information in the last few days, and I really want you to get a chance to kind of work with it a little bit. But the one kind of just little piece of peering into the future that I'll do is that because of the exercise we just did, we realized it doesn't make any difference if we use a left or a right endpoint on our rectangles. Sure, it impacts whether we're talking about inscribed or circumscribed, but who cares? We're just going to turn around and take a limit as the number of rectangles goes to infinity, so they fit the curve perfectly anyway. Big deal, right? The inscribed ones are going to rise up and match the curve perfectly from the bottom. The circumscribed ones drop down and match the curve perfectly from the top. So who cares? The easiest one to do is a right-hand interval. And so then we can say in what's called a Riemann sum, that's our vocabulary word for probably next week, for the next assignment. A Riemann sum is just this. The limit of the sum of f of a plus I delta x times delta x from 1 to n. That's always going to give us the exact area under a curve, which is what we just did. Okay. And the sort of the terminology we use for this right here, a plus I delta x, we just call c sub I. C for convenience. Seriously, the most convenient way to describe the height of the ith rectangle is at its right edge. Okay. All right. And we'll get back to this. I would be very surprised if anybody felt 100% confident with having just complete understanding of this. That would be amazing to me. We're going to have to come back and hit this stuff again and fill in some gaps, but I think you got enough to get going on it.
Okay.
How much time do we have? 10 minutes? Okay.